Here's problem number 2. What is my H naught and H1?
0, 0. T equals 0.
0, 0? Like that?
Rho equals 0.
Rho equals 0?
Rho does not.
And rho does not equal 0. Great. Are we on board?
Yes.
Step 2. Find my critical value and draw a picture. Here's my picture. And what's my critical value? I have no idea. What is this? Degrees of freedom is 5. Is that right?
Yes. 0.754.
Negative 0.754 and positive 0.754. And then step 3.
Test that.
Yeah, so then I'm going to put stat. I'm going to say which one. This is L1. This one's L2. And I'm going to do stat, test. Remember, you got to show your work.
Yes.
Then reg t-test of L1, comma L2. And you guys got R equals what?
0.445.
445. Goes in here. So step 4.
Do not
What's up with step 4, guys?
reject.
Yeah. Do not reject H naught. So is it a line?
No.
Not a line.
Should we put that in there?
So then in step 5, not enough evidence.
To support.
To support claim of correlation between, what are these things?
Size and
Size
revenue.
and revenue. Okay, good. Be on board?
Yes.
All right. Now we're going to take a look at regression. So it's the line of best fit, or least squares line. So in other words, the very center of these dots is your average x and your average y. So x bar, comma y bar. That's the very center. If you look at all the possible lines that could go through that, the line that best fits the data, that kind of matches up with the data the best, that's called our least squares regression line. Why is it called least squares? Because you figure out how far every single y value is straight up and down to that line, and you square all those amounts. I had to do this in college. And then you sum them all up. The line that gives you the smallest sum of all those squares is your least squares regression line. So I had to do that. And then we found out that we could use this great formula, which I'll show you in just a minute, actually. But first, we got to talk about this. It is in color, which means it's really, really, really important. Zach, read.
This line is used to predict the values of y for a given x only used when there is a correlation or relationship.
Okay, so pause for a second. So in other words, you only do this when you have when you reject H naught. In other words, it is a line. Then you use regression line. Keep going.
When r is not significantly different from 0, the best predictor of y is the mean of the data values of y. If not a line, use the average y.
In other words, when you do not reject H naught, then it is not a line. So, for example, shoe size and the number of hours someone watches TV during a week. Do you think those two things are related or not?
No.
Not really. But if you found the data, you'd come up with a line that had the smallest squares. You guys understand what I'm saying? You'd have some line. So are you telling me that someone with a size 14 shoe is going to watch way more TV than someone with a size 2 shoe? Is it reasonable to use this line to predict someone with a size 16 shoe and say, oh, I think they must watch 34 hours of TV a week?
No.
Right? What would be the best guess at how many hours of TV they watch a week? The mean, the average number. So say people on average watch 22 hours of TV a week. Your best guess with someone with a size 16 shoe is 22 hours of TV a week. So, you guys kind of follow what I'm saying?
Yes.
So if it's not correlated, then just pick the average Y, the mean of all the Y's of your sample. Good. If your data is a line, if you rejected H naught, then use the line. That's all good. So like I complained before, we were very, very, very pleased to get these formulas, because at least we can come up with an actual number without having to just beat our heads against and try stuff until we found something that looks better. Where A is your y-intercept, and B is the slope. So y equals A plus bx. It's very similar to y equals mx plus b. You guys have heard that one, right?
Mm-hmm.
This is the same, only your mx they've switched the place of your mx and your b. They've just written them, the number comes first and the x part comes second. So y equals some number plus b times x, where b is your slope. And the nice thing is you guys can just use your TA calculator and the linear edge t-test to find a and b, and you already know how to do that.
Mm-hmm.
So if you kind of look at your calculator, stat, test, oops, linear edge t-test, you'll notice that, notice right here that it gives you the formula, so you have to remember that, y equals a plus bx. It already gives you that part. And then it tells you what a is. If you scroll down, it tells you what b is. And you scroll down further, and then it gives you what r is. Obviously, I don't have data in there right now. But it's all in there. Good?
Yeah.
Great. So just a couple notes. Remember, x is your explanatory variable. It's the one that you can control. It's an independent variable. The y is the response variable or the dependent variable. And this regression equation, y equals a plus bx, it lets you pick either x or y and find the other things. So I don't know if you guys care, but are you guys familiar with the idea of a line? So here's a line. What's going on with this? Why is it not showing up? Okay, or maybe we just won't do that. Well, the line. There we go. So someone give me a formula. So, like I said, 2.4x minus 3.7 or 3.8. Here's a line. So if I slide anywhere along here, I can find different variables. Do you see how it kind of changes?
Uh-huh.
I can pick a number for x, and it will tell me what the y should be at that point. Or I can find a value for x. So if I want y to be 1, I'll go where y is 1. When y is 1, x is, I can't quite get there. Oh, 2, x is 2.
Mm-hmm.
So I can kind of follow what I'm saying.
Yes.
So you can find whether an x or a y. So y equals 3.7x plus 4.2, say. All right. So you guys know how to find y if you're given an x. That's pretty straightforward. But someone give me a number for a y.
For what?
Yeah, like a largest number for y.
12.
12, great. When y is 12, I can figure out what x is. So I just put 12 in for x. 12
For Y.
Or sorry, for y. Sorry, thank you. And then what's the first thing I'm going to do?
Subtract
Subtract
point.
4.2 from both sides. And I'm going to get 7.8 equals 3.7x. And then how do I solve for x?
Divide by 3.7 on both sides.
Divide by 3.7. And you will get x equals 2 point something. Hey Google, what's 7.8 divided by 3.7?
The answer is approximately 2.108108.
108, 2.1. Okay, good. So then when y is 12, x is 2.1. Good. So you can find either one. Now I'll either give you the x or the y and ask you to find the other one. Here's a couple of cautions. Michaela, go ahead and read.
Extrapolations, future predictions. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables, and if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well.
Right. And the scatter plot confirms. So that there is a linear correlation, and the scatter plot confirms that the linear regression line fits it. So here's a couple of others we're going to talk about. We talked about one of these already, which is you can't use a line to predict your data if your data is not aligned.
Yes.
So you guys kind of follow? So it's going to give you the line of best fit, but if your data is a bunch of jumbled dots, then you can't use a line to predict it. Good, otherwise it's going to tell you that someone with a size 16 shoe watches 32 hours of television a week. Okay. The second thing is looking at the scatter plot. And maybe we do that first. So let me show you what they mean by that. This is what they mean by that. So these are 4 sets of data. They all have the same R, linear correlation coefficient, and they all have the same linear regression line. But, so if you're just looking at your numbers on paper, they would seem exactly the same. Except that when you graph them, you can see that first one is what you expect to get, right? But this one over here, it's totally not a line. It's a curve. It's like a parabola. So that line doesn't match it at all, right? And it's kind of a bad thing to use. This one here, you guys see that outlier? Right, so if you kicked out that outlier, then you get something that kind of goes more like that. You know what I'm saying? And then over here, there's totally this outlier here. This should be straight up and down. You see what I'm saying? So it's possible to kind of warp the data that way and kind of twist things around to make them kind of work. So you have to kind of, it's important to do a scatter plot and kind of look at it and see and make sure that the line kind of jives with what's going on, or that what you have going on is not something weird and funky with these weird outliers. You can actually do that. We'll do that later, actually, once you get some data in there. I just wanted to kind of point that out. So that's what they mean by that part, about that part there. The other part is, is this here. Here's another warning. So if you predict too far beyond your data, then you're subject to be in trouble. So for example, say we look at cell phone usage in the last 20 years, and we say, oh yeah, it's totally going up, cell phone usage over the last 20 years. Do you think that I could possibly predict what cell phone usage is going to be in 2150, over 100 years from now?
No.
Right? Like they won't even be using cell phones. It's like old technology. So you can't really go too far in the future. You got to kind of stay restricted. We might be able to predict like 5 or 10 years. You know what I'm saying? But we're not going to be able to predict like 40 years from now based upon 20 years. And then again, a reminder that if your data is not correlated, in other words, if you did not reject H naught, then it's not a line. So just use the sample mean to predict. That's your best guess is the sample mean. I know I'm hitting you guys over the head with this, but people screw this up all the time, so that's why I'm saying it a million times. Hoping that one of them makes sense. All right, so here, again, if you reject H naught, it is a line. So then you're going to use y equals a plus bx. If you do not reject H naught, then it's not a line, and you use y equals y bar. That's your best guess for y. And x equals x bar. That's your best guess for x. You're trying to predict x or y.
Sounds legit.
Oh, good. Looks like people are writing stuff down. You guys a minute. Alrighty. So see, my R is 7, so there's a positive correlation. It's kind of like a line, so you would use the actual line. That's the best predictor. If R is equal to 0, then our best predictor to use is just a straight, is just whatever the mean is. No matter what X is, my best guess for Y is whatever Y bar is. If we have a line this way, then I can use the line again to predict. Because if R is -7 over here. Okay. Here's an example. So I think this is at the bottom of your page. So here I'm going to use alpha equals 0.05. So what is my alpha is 0.05? Let's see, my degrees of freedom is 4. What's my critical value? Degrees of freedom is 4. What's my, I don't know what my critical value is. What's my critical value?
Point 811.
Great. 0.811. Negative 0.811. And my R is what? So they told me my R is, they didn't tell me.
0.98. Not 9.82.
0.982. Did they tell you?
Yes.
Okay. So if my R is 0.982, it's going to be right in here.
Yep.
Is it a line or not a line?
Line.
Great. So now I can use my linear regression line. So it is a line. So I can use my y equals a plus bx. So I'm going to put that stuff in to y equals a plus bx. So let's go ahead and do that. So we're going to go to our calculators, and I'm going to put in stat edit, and I'm going to put my data in there. What do I got? 63. You guys have it, right? 63,
Yes.
29, 20.8. So we've got the calculators out. They're all putting it in.
Yes.
Would you throw out A?
We've got the graphs for us to take a look. So go ahead and put them all in there, and then we can graph it and take a look. See what we've got. Okay, so then double check your data. Whenever we're going to be using a calculator almost exclusively for chapters 10 and 11, which means if you type something wrong in your list, you are SLO and you have no idea. So double check your numbers. Make sure you're good. Okay, looks like mine are fine. And I'm going to do stat, test,
Mhm.
linear reg t test.
Mhm.
L1, so your X is L1, my Y is L2. Frequency, leave that as 1. That's always 1.
Mhm.
For this part, it's always not equal to 0, always.
Mhm.
Leave this reg eq empty and hit calculate. So now my A is 0.396. 0.396 plus my B is 1.106x. So this is what I've got. And then I want to predict for increase of 40,000 cars. Okay, so 40,000 cars. Is cars my X or my Y, guys? It's my X. You guys see the little X and Y up here?
Yes.
Cars is my X. So when X is what? So cars in 10,000s. So 40,000s would be when X is what?
4.
4.
40.
Does everyone understand that?
Yeah.
It says cars in 10,000s. On the test, I'm going to give you something more straightforward. It'll be just the number. So cars is 4, because cars, it's cars, so cars is my X. So I'm going to put in 4 for X,
Mhm.
and figure out what my Y is. .396 plus 0.424, so 0.820. So I would say that you would make $0.820 billion, $820 million, if you had 40,000 cars. That's my prediction. Okay? You guys do lab problem number 5.